Okay, I think if you've paid attention, you've done all the work, you've read, you've taken notes, I think you'll rock the test tomorrow. Personally, some of you will struggle because sometimes this class just doesn't click for some people. 2 of you will be done in 20 minutes and think where the real test is, and then the rest will be somewhere in between those two. So anyway, today we're going to wrap up ionization energy, which we talked about a little bit already. Welcome. I don't have any work for you, so just chill. If you haven't done the Chapter 7 Ed Puzzle and Blue Sheet, please do that. And then Chapter 7, the last few sections, that's a lot of reading. And I'm just going to tell you right up, there's nothing on the test from it. That's all I'm going to say. Okay, next. To help you prepare for this test, there's a bunch of things. They're not new, but you could watch the recording today. We'll probably, towards the end of the hour, go over the test while I record. Next, the practice test on Canvas. All right, the practice test, there's, I think it's in the Chapter 7 is where you would find it, and it has the answers underneath it. The Chapter 7 review videos are really good. They work on the phone, actually, without actually having to go to YouTube. That's rare. But I take a periodic table, I put all the arrows, we label it, and we give the reason for each one, which is what you have to do. Pretty much all of Chapter 7 on the test is the arrows and then why. All right? The Chapter 6, class videos. If you remember the very first day we did Chapter 6, I showed you a problem and I said what? This is the test problem. We also did that problem another day. That's in there somewhere. Word for word. The only thing that changes is the length of the nanometers. Okay? So you can find that. Or, heaven help us, you could look in your notes and look at that exact problem that somewhere you wrote. Hopefully this problem is on there. All right? Chapter 7 con videos. I noticed this morning I had never actually published that page. That is not an assignment by any means. I published it now. There are 6, 10 to 15 minute videos on Khan Academy on everything about Chapter 7. It used to be how we would learn Chapter 7, but we didn't get there in time. And then there are 3 videos on Ed Puzzle. One of them is not assigned. The other 2 were. I may, if I put more on there tonight or this evening, whatever, it would really be during my prep hour, next hour. If I put anything new, it's not an assignment. It would just be possibly helpful to you. Sound good? And then the book and your notes. There's a ton of materials out there for you to study for this test. Okay, next. We talked about ionization energy, didn't we? Okay, so just a review. The ionization energy is the energy required to remove an electron. The second one is to remove a second or third or fourth or fifth. All right, it requires more energy to remove each successive electron. And that was because as we removed an electron, then the ion became positive. If we wanted to remove another electron, it's now positive, so it's harder because it's more attractive to the electron. We remove that second one, now it's even more positive. And now it's harder to remove a negative. Eventually, though, we get to a place where there's a very large jump in energy. Will you see if you can remind your lab partner where that big jump came from? All right, good. I heard some words that sounded good. All right, so the big gap comes here, here, here. The big jump comes when the electron you're going to remove is a core electron. Hopefully you said that, or a full shell. I heard that in the back row. Test question. I'll just straight up tell you. the test question gives you a series of numbers, and let's just say it's like 1, 2, 6, 58, and it's asking you what family this thing probably lives in. How would you figure that out? The big jump. Where's the big jump? All right, well, after what? After the third. That means this thing is probably a member of the third family. Because it took energy to remove the first, energy to remove the second, took even more energy to remove the third, but then a humongous jump in energy. So this would be like aluminum. Al plus 1, Al plus 2, Al plus 3. Those are acceptable and reasonable, but once we get to here, Al plus 3 is just like neon, and now we're in trouble. Yeah, Adrian? I don't think so. Hold on. Yeah, this is fine because it took this energy to make it a plus 1, plus 2, plus 3, and then it would be a plus 4, which it won't, which is what it would be if it was in family 4. Does that make sense? It's a good question because it's a little tricky to get. Are we okay with the big jump comes when we remove the core electron? Okay, good. Next, we had the trends. It decrease as we go left and lower. Did we have that anywhere? All right, it decreased as we went down because the size of the atom got larger. The bigger the atom, the easier it is to remove an electron from it. Okay, and we know size, that trend we accounted for by adding principal energy levels. We okay with that? All right, how come it was high over here? Go ahead, Diane. Because they're really small. When you're really small, the electrons can be very close to the positively charged nucleus. That creates a very strong attractive force. The stronger the attractive force, the greater the energy required to break that attraction. Good job, Diane. Are we good? This all should still be review, I think. I think the next slide is about where we, I think this is where we ended. All right? So, generally, as one goes across the row, it gets harder to remove an electron. And here's the explanation again. As you go from left to right, Zeph increases, which causes the atom to get smaller, which means there's a greater force attracting the electron to the nucleus. Okay, we good? All right, so why do metals have low ionization energies? I'm not going to spend a ton of time. We take 30 seconds and ask, we'll uncover that, but ask your partner, discuss that. Why do metals have a low ionization energy? You got this, Weber? You got it? Okay. Okay, let's call that good. Because they have low effective nuclear charges, which makes the outermost electron less attracted to the nucleus and therefore easier to remove. You could certainly say they're bigger because it's all tied into one nice little nutshell, right? Okay. Zeph affects size. Zeph affects ionization energy. It affects pretty much everything. When in doubt tomorrow, if something's getting smaller, the answer is Zeph. If something's getting bigger, what do you think it is? What? Nope. N or electron-electron repulsion. Okay. Account for the large jump in ionization energy seen above. We just kind of did that. We are now trying to remove a core electron after the first two have been removed. You okay with that? We're not going to spend time on that one. All right. However, there are two apparent discontinuities in this trend. Because it's chemistry, there is always a pain in the butt. But wait a minute. And that's what we have here. So you will notice that as we go left to right, so this is just, we're going along across the rows, not up and down. And then there's these dips. Okay? And they get really, really weird. But don't stress. You don't need to know every little minute detail, but you do need to know the following. All right, the first discontinuity. Discontinuity means when it doesn't follow the trend we expect it to. The first occurs between groups 2A and 3A. So what the A, we've never heard that before. If you look at that periodic table, when we talk about groups 1, 2, 3A or whatever, we're talking about the periodic table as though the transition metals don't exist, which is kind of how we have for a while. When we say family 3, we've been talking about boron, aluminum, gallium, right? Technically, that's 3A. If we said 13B, that would be included in. All right, so anyway, what we're saying is between like beryllium and boron, there's a little dip, and magnesium and aluminum, there's a little dip. And this is not that hard to explain. The electron is farther from the nucleus, all right, and the small amount of repulsion by the s electrons. So what they're saying, if we draw these boxes to represent our s and p's, we're talking about from here, this follows what we expect, but this third one is a little bit lower in energy than we would expect based on the trend. And so look, here's your explanation. It requires slightly less energy to remove this electron from the P because it is both farther from the nucleus and it's pushed away a little bit by the S. Okay? So like, that's a reasonable, of all the weird things I've explained, this one's not that bad, I hope. Okay? So, we're saying that it's easier to remove that than we would expect it to, just following the general trend. And that's, if it's easier to remove, whoops, I guess I already drew that arrow. That's why we had that dip in ionization energy. Okay? What's that? Yeah, that's the next slide, and it's pretty easy to understand in my opinion too. Okay. The second one occurs between group 5 and 6. So 5 and 6, we're now talking nitrogen and oxygen. And this one, the electron removed comes from a doubly occupied orbital. Repulsion from other electrons in orbital help in its removal. So now we're about, we have 1, 2, 3, 4, 5. So that would be nitrogen, right? If we throw in the sixth one, we're now talking about oxygen. And what this is saying is it's a little bit easier to remove this red one it to be. But that's okay, because if you think about it, we've now forced two electrons to be pretty close together. Electrons do what to each other? They repel. So it requires slightly less energy to remove the red one than we expected, because it is repelled and it's in an already occupied level. Kind of okay with that? When in doubt, use the term electron-electron repulsion. Okay? So those are your two dips. And they have to do with either adding an electron to this empty P or when you pair your first pair in your P. Okay, and these are in the book fairly clearly explained as well. All right, so here's that summary. I noticed Benson tore hers out and put it to the left, right? Here's the summary page. we've added. The white you already have written somewhere, I hope. The black we've added. Metals have low ionization energies because they have low effective nuclear charges. That affects their sizes as well, which definitely it goes along. Nonmetals have high ionization energies because they have high Zeph. All right? Do you notice something? Because I have been saying this, and you have to do this on the test. You need to know the relationship, whether it's directly or indirectly, or inverse or direct. If this is low and this is low, how are they related to each other? Directly. Okay, remember that for tomorrow. If they do the same thing, they're directly related. If one goes up and one goes down, then we call that an inverse relationship. All right, so these are both high again. So ionization energy and Zeph are directly related. Okay, next. Ionization energy increases as you take off more and more electrons because you are removing an atom from an increasingly positive, this should be, yeah, an electron from an increasingly positive atom. We said that a few times, right? As we remove an electron, it becomes a positive ion. That makes it even more hard to remove a negative from the positive. Okay, and then ionization energy takes a quantum leap when you try to remove a core electron because you are breaking a completed shell. All right, we good? I did not put the discontinuities up there. Those are something you should know. I don't even think I have a test question on them, but they are things that you need to know. Okay, the final nugget of our entire unit is electron affinity. I see some kids writing one or two. Let's take a, okay, 99% of Chapter 7 tests can be summed up on that screen if you've been writing them down. Okay, the last one we're talking about is electron affinity. And as you can see in my beautiful handwriting, of these things, it's the least important. There's one electron affinity question. So, I mean, you'll see the test format. How many letters are between A and H? 8? There's 8 things on Chapter 7 that you have to explain, and electron affinity is one of the 8. It's the energy change accompanying addition of electrons to gaseous atom. It's a weird sentence. Whatever. If you read that carefully, you might notice it's the exact opposite of something. It's the exact opposite of ionization. Ionization was the energy required to remove. Now this is defined as the energy that's going to be given off when you add an electron to an atom. Now, electron affinity and electronegativity are similar to each other. They are not the exact same thing, but they're close. Electron affinity is literally the energy given off when an electron moves into an atom and gets closer to the nucleus. Electronegativity is the ability of the atom to attract. They're related, but they're not the same thing. All right? So, when we have an ionic substance form, we have a metal that loses and a nonmetal that gains. And so we have ionization energy and electron affinity balanced out. Okay? Because the electron literally leaves and that is accepted by something else in an ionic compound. All right, in general, and these are general trends, electron affinity becomes more exothermic as you go from left to right across a row. That's a little weird written, but the more negative it is, we would say that's increasing because it's the energy release. Are you okay with that? Whenever we start throwing a negative into something and we say more and less, that can get confusing. But the more negative it is, the more exothermic or energy is given off. So it would make complete sense now that we have the high numbers in the right-hand corner, because these have the highest Zeph, right? And it would make sense that down here we have the least negative values, because those are the metals. They don't want to gain an electron. They can. They're still exothermic values. They can, but they're significantly less exothermic than the nonmetals. All right? If you look at the noble gases, you will notice that they're all positive values. It requires energy to add an electron to a noble gas. That's why they don't. They just don't. There's going to be some explanation coming up, but I can't even remotely explain to you why magnesium and a noble gas behave similar. I don't think anyone can, because that's like, what? Right. Well, we would say they're noble subshell. We'll take it. Sir Boyd. But it's not that way for everything. And whatever. Chemistry is just, it's awesome in its vagueness sometimes. All right. There are, again, however, two discontinuities in this trend, and it's what Boyd's pretty much pointed out. All right. The first is between groups 1 and 2. All right, the added electron must go into a p orbital, not an s orbital. All right, electron is farther from the nucleus and feels repulsion from the s electron. And these are in the book again. I don't want to spend more than the next couple of minutes on these. But all it's saying is if we had to add here versus here, it's kind of weird because we're talking about moving it to the right one space. You with me? That's why that arrow is there. What we're saying is this is less exothermic than this would be or this would be, because once again, we're now going to have to add to the P instead of just completing the S, which is farther away. And our good friend, what? Electron-electron repulsion comes to play again. Okay, we will come back to this slide in a second. All right, the second occurs between group 6A and 5A. Do you notice that these are similar to ionization energy? They're just reversed, because electron affinity and ionization energy are the opposite of each other. All right, this time group 5A has no empty orbitals. Extra electron must go into the occupied orbital, creating repulsion. There's our friend again. It's right here. The trend exceptions are not on my test. I've never seen them on the AP test either. But feel free to read a little bit about electron affinity and their discontinuities. Okay. That's it. There are a bunch of other slides. They're the properties of families, and you should read those. They're not on the test. All right, so let's talk about the test. Don't write this down because this... No, we're good here. Okay, let's just have this up here. So we have, it's 8:19. We're ahead of where I thought we'd be. This is essentially, now they're different, but this is exactly the test. Like I've changed larger for the word smaller or something, or I've changed the atom that I've talked about. But this is the format you will get for Chapter 7. Chapter 6 is completely different, but this is for Chapter 7. Says use details from the modern atomic theory periodicity. Periodicity is just the trends we've been talking about. It's how things change in a period on the periodic table. Okay? Or electron configuration to explain why. So if electron configuration and atomic theory are in here, there is some chapter 6 and 7 accounted for here. So atomic radii become larger as the atomic number within a family gets larger. When I'm in a meeting, I hate when someone reads to me something I can read myself. So I'm going to pause this, take a couple of minutes and read through this. Do not take pictures of it, but you can take as much notes as you want. This one's not hard, like you get it right. But I'm just looking for why it's Mg and O. Like not an Mg2O, not MgO2, why it's just MgO. And I'm looking for something to do with its electron configurations. You okay with that? If you're not, look it up. Although if you Google why is it MgO, like it's big, what are you talking about? All right. Now, let's talk about chapter 6 test question. I don't even think it's on here. I'll just print it and sort of read through it. Oh, there are, I won't leave this up there very long, but there are, so here's the EFG, then there's some things about Zeph and being what type of proportionality, and then this is just explaining your 3 arrows essentially. You have to arrange these in order of size. That's actually harder than you think. And then there's that question about the ionization energies. You have first one reasonable, second one reasonable, third one gigantic. Okay, so there's the chapter 7 piece. This is actually a different version. Let me double check. Hold on. Shoot. That's from years ago. But I'm pretty sure they're the same. Okay. So I actually, on this version, the hardest one is not there anymore. Merry early Christmas. So that one's still there. This one's still there. And that one is still there. But the one where you had to rank them in order, which was hard and took a long time for you to kind of figure them out, I took that one off, looks like. Okay, chapter 6, you remember this math question, I hope. Okay, it will be exactly the same. This one says 454. The one we practiced, I have no idea what it was, but it maybe even if it was 454. I will most likely change that number here in about 20 minutes. All right, which of the following is a valid set of 4 quantum numbers? If you remember the quantum number rules, I'll shrink this down for a second. But quantum numbers, you had n, which could be any whole number that had to, it couldn't be 0, right? All right, and then you had L. Yeah, L, and that had to be at minimum 1 less than n, correct? And then you had ML. Was that the next one in the notes? Am I going in the right order? Okay. ML was positive M to negative, sorry, L. It's hard to think it through because they're so, whatever. So ML was negative L to positive L, including 0. And that was the one that told me the number of orientations in space. And then spin was MS, and that was just positive or negative 1/2. You all right with that? You should have written those down somewhere. So all you have to do is you find the one that breaks one of those rules. To me, and I mean, I wrote it, and I've learned this forever. To me, easiest questions on the test. It's this one. All right, there are blank subshells in the second shell, or n equals 2. That is also a quantum numbers question. You have to tell me when light is released from an atom. This is an important thing to know. When is it actually released? It's when an electron does something. You need to know what that something is. And then there's directly and indirectly again. All right. The electron configuration full and noble gas for the following elements. N is an absolute piece of cake, I hope. V isn't too bad. There was a third one, which was way long, and I deleted that for time's sake. What? No. And then this also is math. So you should know E equals hc over lambda. You should know E equals hv. And V is what? Frequency. Okay? So you should know those, and you can solve all of these. Okay. That's that. Questions for me? Now, will you please remember, I record this, and then I save it, and I put it on Canvas. Okay, I'm done. We have like 10 minutes, 11 minutes. You can work on the blue sheet. You can.